Okay, welcome back, you guys. Once again, I hope everybody's doing well. Please be safe and take all the precautions. This is a virus, so it multiplies exponentially. I hope everybody's healthy at this point. So in the last video, we left talking about inferential statistics and trying to figure out a population, what a population looks like by taking samples, although in the last video we were just taking out single blocks and trying to figure out how would that help us know about the underlying population. And so I think I mentioned at the end of the last video that really what we want to do is look at samples bigger than one. I talked about my golf scores. I hope you don't mind that. We talked about Bob's reaction time and the fact that he may want to do that task multiple times to show what his population looks like, right? What his reaction time looks like. And so I have my trusty bag again. This is those 25 blocks that have the characteristics that I showed you before. It has a mean of 14. The lowest score was 10. There was one of those, and then 2 11s, and then 3 12s, and so on and so forth. You can go back and look at that if you'd like. Hopefully, maybe you took notes. That would be a good thing. So I want to do more than taking out a single block and show you what this looks like, what happens. Okay, it's really kind of cool. I think I'm a stats geek, right? But it's a fairly complex concept, but it's going to set us up for the rest of the course. And actually, once we get this done, we're going to be focusing much more on kind of practical statistical tests of significance. We can test drugs, or we can test effects of background music on how people perceive the quality of a movie, for example, or we can look at how making a solution certain colors might change how people perceive the taste of those solutions. I think it's pretty cool, but we have to wait. We have to do the basics here for inferential statistics before we can make that move, okay? So here's what I'm going to do. And if we were live in class, this works so much better, but we can make it work this way as well. You just have to think. Remember, I'm going to make you think. I'm going to take out samples from this bag, and if we were live, I would pass the bag around and say, okay, you take one, you take one, you take one, you take one, okay? And what we're going to do is we're going to take out a sample, more than one. In this case, we're going to do samples of 4, and I'm going to use that word in its plural. We're going to take out multiple samples of 4. Samples of 4, okay? That is, we're going to take out 4 blocks, and that will be our sample. What we're going to do then is, for each sample, we're going to calculate the mean for that sample, okay? And this is where we're going to use M as our symbol for the mean. Remember, if we have a population, we use the symbol mu. In this case, we're going to use uppercase M as our symbol for a sample mean. So we're going to have multiple sample means, okay? And this is a number line here, okay? This doesn't represent individual samples. You'll see how this unfolds in a minute when we start doing it. This is why it's important to actually do it. When you read about this in the book, it's going to be very confusing, okay? It's just the nature of the beast in a way. So I'll show you how this works, okay? I need to get a piece of paper and a pen. So what I'm going to do, oh, where's my pen? Hold on. Okay, sorry about that. So here's what I'm going to do. Virtually, we'll go into this bag and we'll take out a sample of 4, okay? And let me just give you an example. This is why I'd rather actually do this, but that's okay. We'll figure it out, okay? So let's suppose the first 4 blocks that we take out look like this: a 14, a 12, a 15, and a 14. Remember, when I put my hand in there, the most likely thing I'm going to pull out is 14. By definition, there's 5 14s. There's only 4 15s, and so on and so forth. There's only 1 18. When I look at this, it's not surprising that I didn't get an 18. That is an improbable pick, but not impossible, right? 4%. Everybody with me? You might want to look at that original distribution, okay? But suppose I take out these 4 blocks. What I'm going to do is I'm going to calculate the mean for these 4 blocks. You can check me if you'd like. Mean is 13.75, okay? What I'm going to do now is I'm going to plot that on this curve. So here we go, okay? Here's a mean of 13.75. So these are values of, possible values of the mean. This would be equivalent to my x's. This would be equivalent to my x's here. In this case, it's just values that represent the mean, okay? And I put 13.75 there. That's the position on this number line, okay? So that's my first sample of 4. Here's my second sample of 4. And I thought about this one because we did pick out the 12 yesterday and we picked out the 15. So it's like we started our sample. And then 13 and 14, okay? Calculate that mean. The mean in this case is 13.5. So I'll put 13.5 here, okay? It's lower than 13.75. This is just the number line, okay? Let's take out our third sample. 13, 13, 12, 14. Notice we're getting these numbers because those are the most probable numbers to pick from the deck, okay? It'd be like if you had a deck of playing cards and there were 3 times as many diamonds as there were clubs. And when I'm picking cards out, I have a higher likelihood of getting a diamond because there's 3 times as many, okay? Now, normal playing cards, of course, the suits are equal. But if there was more diamonds than clubs, I would have a higher chance. Same thing here, more 14s than anything. So I see that again. I see some others that are close. Here's the mean for this sample of 4, and it's 13. So I'm going to put that 13 here. Okay. Let's look at another sample, our 4th sample. And now, in this case, I decided, hey, what if we pulled that 18? It's going to happen 4% of the time. Fact, okay? Because there's one of the blocks that is 18 out of 25. So suppose we've got a sample like this, 14, 16, 18, 12. We're going to calculate the mean. Again, this is an M. Mean is 15. That's not surprising because we had an 18 there, we had a 16. So let's go back to our graph, and here's our sample with a mean of 15. Okay? I'm going to keep doing this. I'm going to put, once I take my sample of 4, then I'll put those back in the bag and kind of mix them all up, randomize them, and take out another sample of 4, calculate the mean, put them back, randomize, take out another sample of 4, calculate the mean, plot that, put it back in the bag, mix them up, take out another sample of, I could do this for a long time. I'm hoping you're getting the point. I'm going to do this in a way, hypothetically, I could do this an infinite number of times. Boom, take out a sample, take out a sample, take out a sample. Each time I do that, I'm going to plot the sample mean. Everybody got it? I'm going to do that, I'm going to do that, I'm going to plot the sample mean. So sometimes I'm going to get another 13.5 and another 13.75, and I'm going to get a 14, and I'm going to get another 14. That is a mean of 14, okay, for a sample. And then I'll get a 13 or a 12.5 and a 13.5 and a, so on and so forth. And once in a while I'll have a 15.5. And I'm going to start developing this distribution, okay? But this is not a distribution of x values. I repeat, okay? It's not a distribution of single values, of x values. This is a distribution of means of samples of 4. I'm going to repeat that, okay? So this is a distribution of the means, that's why I have m's here, okay, of samples of n equal 4, okay? So, in fact, this should be a small n. Sorry about that. That's small n. The name of this thing is the sampling distribution of sample means. I'm going to underline the S there. This is a whole bunch of sample means where n equals 4. That is means from a group of 4 blocks from the bag. Get those numbers, find the mean. Each sample is represented by one block. Here's a sample, here's a sample, here's a sample, okay? So each group of 4 blocks we calculate the mean. The mean is what goes on here, okay? Everybody with me? Here's a couple more samples. Let's take out this sample. Now, I put this one in here because this is a curious one, right? I'm most likely to pick out 14. That's a fact, 20%. Highest of any of the values, okay? 14. All of a sudden this 10 pops up. Wow. Well, once in a while, I'm going to get a sample that includes the block that has the value 10, okay? Then I pick out another one, it's 14. Then I pick out another one, 18. Oh my God, wow. This was a very improbable pick, but it happens. Wow, this is an improbable pick, but it happens, okay? Probable. When I calculate the mean for this sample, the mean is 14. Very interesting because this is a very extreme score, right, from our original population, as is this. But they came together, and when I do the calculation for a mean, it's 14. Huh, interesting. Here's another sample. 15, 10, wow, that was unusual. 13, what I expect. 14, most expected. Calculate that, get a 13. So I put this 14 up here. I mean, here's where that sample was, right, 14. 13 down here is where that sample was. Okay? So, putting my hand in, taking out a sample of, in this case, 4, and calculating the mean for that sample. Each sample of 4 blocks. Going to calculate the mean. That becomes one of the blocks here in this distribution. Okay? Just give you a minute to think about that, honestly. And I'm going to ask you to remember this, and unfortunately, when I do this during the semester, we take an entire class period to pull out samples, and plot the means of each sample, plot the mean, and we do different sizes and so on and so forth. And oftentimes students are like, yeah, okay, we get it. Well, I want people to have what I would call a strong memory of this, because I'll be referring to this later, and I want people to remember exactly what's happening, because it's sometimes confusing, right? If I take out a sample of 10 blocks and find the mean for those 10 blocks, those 10 blocks then only represent one block in this sampling distribution of sample means. Another kind of a frustrating thing for me as a teacher is that a lot of people want to shorten the information down, like shorten it. Can I say it in one word? Can I say it in 2 words? The answer is absolutely not in this case. This is a sampling distribution of sample means. It's not just one mean. There's a whole bunch of means here. It's a sampling distribution of sample means, and these are means of samples of 4. Okay? Because it's going to be important to specify how large the sample size is. But we're going to do 1,000 of these, okay? 1,000 samples of 4, and each one of those will put the block for the mean, okay? I don't want to really overdo this, but it's kind of important to understand what we're doing here, okay? Taking a sample of 4 from this bag, calculating the mean for that sample, plotting that as one block. Go in, take out another sample of 4, calculate the mean, put that as one block, that is one mean on this distribution. Okay? We're going to keep doing that, keep doing that, keep doing that. Okay? It's called the sampling distribution of sample means, where the sample size is 4. Because when we do larger samples, things are going to get interesting. Okay, but it's the same procedure, Okay. Hopefully everybody has this, because now I want to show you what happens when we have different size samples. Let's do this. Okay. Can we see this? Let me hold this up a little bit closer. Okay. Here's our original population. So these would be X values here. These would be X values here. I made it small because we're going to move to other, to our sampling distributions. I'm hoping that you can see that. Okay. 5 14s, 4 15s, 3 16s. Okay. Look at your notes. Hopefully you're taking notes here. All right. Now what we're going to do, just like what I told you, okay, just like we went over, we're going to do sampling distributions. And in this case, so this is going to be M down here. These are M's. Okay, these are M's. These are M's. That is values for the mean for each sample. So these are sampling distributions of sample means. Okay? Sampling distribution of sample means. That's why on the x-axis here we have m's, all right? And what I'm showing you here is, sorry, there we go. What I'm showing you here is we're going to have 3 different sampling distributions of sample means. One where the n is equal to 2, one where the n is equal to 4, one is where the n is equal to 8, okay? And I'm going to write on here, this is samples, or let's do this, sample means, because it's multiple. I'm going to make this distribution, okay? Now, let's go back to our original distribution here, okay? As soon as I take out more than one, that is more than one block from the bag, it would be impossible for me to have a mean of 18 because I'm taking 2 blocks, right? So even if I pick out the 18, which would be very improbable, that only happens 4% of the time, remember? So put my hand in there and taking out an 18 is kind of a rare thing. I mean, 4% is pretty low chance, okay? Take it out, I get an 18. So I put my hand in to take out the second block. Let's say I picked out the 17. Wow, that's pretty weird because chance of taking out the 18 is only 4%. The probability of taking out the 17 is 8%. So I have to have an improbable event followed by another improbable event. And the math that goes with this, by the way, 4% to pull out an 18. And again, I don't want to sort of dwell on the math, but just to let you know, the chances of pulling out an 18 are 4%. The chances of pulling out a 17 is 8%. When you multiply fractions, they get smaller. And so the chance of pulling out both the 18 and the 17 at the same time is actually 0.0032. It's actually lower than pulling out the 18. That is, to get the 17 and the 18 at the same time. But it's not 0, very improbable. If we pulled out the 17 and the 18, what's the average for that sample? 17 plus 18 divided by 2 would be 17 and a half. So it's right here. Okay. That would be a very unusual event, very rare. Okay. What I want to show you here, though, is that for a sample of 2, it would be impossible to get a mean of 18. It can't happen because there's only one 18. So the 18 is always going to be put together with something lower than 18. So it's going to bring this in a little bit. This is the most extreme mean that we could have for a sample of 2. We go down to the other end of the curve and say, listen, if we picked out that 10, 4% chance of picking out the 10, right? And we picked out the 11 at the same time, a very unusual event has just taken place, okay? 10 plus 11 divided by 2 is 10.5. So here would be the lowest possible sample mean when we have a sample of 2. This would be the highest. This would be the lowest. Okay? And it would be very rare for that to happen. Less than 3% of the time. Most of the time, we're going to be picking out blocks that have numbers like 14, 15, 13, 14, 16, 12, right? All of those. If I took out a block of 14 and a block of 13, then my mean would be 13 and a half, right? And if I took two 14s, it would be 14. And, you get the point, I hope. We're going to start doing this, and what you would see is a bunch of piling up of sample means in here. Most of them are going to be in between 17 and a half and 10 and a half. And in fact, this is very frustrating because we would do this in class and you would see this happening. We would take the whole class period. I'm not going to do that here, but I'll take my time to explain it. When you do this, what you will find, if you did it 1,000 times, I never do it 1,000 times in class. If you do this 1,000 times, what you will see, what will happen is the mean, I'm using mu here, the mean, I'm going to subscript it with an M. That's telling me, right, let's take this slow. This is the mean of the distribution of sample means. You cannot say that in a shorter way. This is the mean, the overall mean of all the sample means of n equals 2. That's what mu sub m is. The subscript here is telling you these are sample means. I'm getting the overall mean of all the sample means. This will equal 14. It will. I'll show you something either later in this video or the next that will help convince you. There's lots of stuff on the internet about this. You can get animations that show this the sampling distribution of sample means. I'm always, when I watch those things, I'm like, well, I don't know, I mean, they can manipulate it any way they want. That's why I do it very low tech in the classroom to show you that this really develops, okay? And what you would see is this would be a normal distribution. This is a normal distribution of means of samples, and it will be centered at the same place that the individual scores were centered. Okay. Let's move to a larger distribution of sample means, and that is where the samples are n equals 4. We just did that on the other page, right? We took out samples of n equal 4, and I showed you some possible outcomes of that. I want to start by saying, well, if you took out samples of n equal 4, taking out 4 blocks from the bag, what would be the lowest possible sample mean that you could get? And if we were doing this in class, I would wait and I'd say, okay, you guys, tell me what is the lowest possible sample mean that you could get with a sample of 4. And oftentimes this stumps people because you have to think. Let's think this through, right? Here's the original population. What would have to occur for me to get the lowest possible sample mean for 4? Well, what would have to occur is I'd have to get the 4 lowest blocks, that is the 4 with the lowest numbers, right? So I would have to pick out the 10, that's a must. I'd have to get the 2 11s, that's a must, and I'd have to get the 12. So my sample would look like this: 10, 11, 11, and 12. That would be the lowest possible sample of 4 of those blocks. This only occurs 4% of the time. This only occurs 8. this occurs 8, and then this occurs only 12% of the time. So this is a very rare sample. We could do this 1,000 times. I would bet you $100 that you wouldn't get this sample. If you randomly took out samples of 4, if we did that 1,000 times, I would bet $100 that we wouldn't get this sample. It's really rare. If we did, what would be the mean here? The mean would be 11, 10 plus 11 plus 11 plus 12 divided by 4. So here it is. Okay. I want you to notice something here. Single scores, there certainly is a 10 there, right? We could pick out a 10. If I took out a sample of 2, we could never have a mean of 10. The lowest mean would be 10.5. If we took out a sample of 4, we could never have a sample mean of 10. The lowest would be 11 in this case. Okay? Same logic here. What would be the highest possible mean for a sample of 10? What would be the highest possible mean for a sample of 10? Well, we'd have to get the 18. We'd have to get both 17s, and we'd have to get the 16. All right? If we did that, the sample mean in that case would be 17. And that would be a very rare event. Most of the time, when we pick out a sample of 4, it's going to include a 14, it's going to include a 16, it's going to include a 13, it's going to include another 14, it's going to include a 15. I mean, once in a while, a 10 will come into those samples. I get it. That'll make it a little bit lower. But here's what the distribution of these sample means would start looking like. They would be in between 11 and 14. And in fact, we'd start to see them piling up like this, okay? What do you think the sample, excuse me, let's go back. What do you think the mean of this distribution of sample means? What do you think the mean of this distribution of all the sample means would be? And you probably would anticipate the correct answer. It would be 14. Okay, that's a 14.00. If we took out samples of 4, and we start plotting the sample means, sample of 4, sample of 4, sample of 4, sample of 4, getting all those means and plotting those numbers, they're not all going to be 14. I should point that out. Same thing here. They're not all going to be 14. They are not all going to be 14. We know that, okay? But the overall mean for all the sample means of 4, the overall mean of this distribution of samples of 4 is going to be 14. This is the symbol. So mu for the population, because we're going to do 1,000, we're going to do 10,000, a million, okay, infinite of sample means. That's why this is a subscript, okay? Mu with a subscript of m tells you this is the mean for this distribution of sample means. It's like, oh, Dr. Specht, what means, and means. Okay, well, take your time. Stand still, okay? Take your time. We're going to take out sample mean. We're going to calculate the mean of that sample, plot it as one block here. Take out another sample of 4. Calculate the mean, put that box up there. Take out another sample of 4. Calculate the mean, put that box up here. You'll start to see this distribution of boxes. The mean of this distribution of sample means will be 14. Okay? And the distribution will look something like this. the center of this distribution is 14. Center of this distribution is 14, 14, 14. Okay. This is the group of individual x's. This is the original population. There's only 25 blocks, right? It's what's in the bag. Take out samples of 2. Take out samples of 2. This is what's going to happen. Take out samples of 4. This is what's going to happen. Both of these are going to have a mean of 14. Let's continue the progression. Let's continue this progression. Okay. Let's do samples of 8. Okay, everybody got it? Samples of 8. Same thing that we're going to do here. Take out a sample of 8 blocks now from the bag. A sample of 8 blocks. Calculate the mean. See, this is calculating the mean. Calculate the mean for those 8 blocks. So sample of 8 blocks gets 1 block in this distribution. Okay? Gets 1 block in that distribution. Put them back in the bag. Take out another sample of 8. We'll plot that mean. Okay? And so on and so on and so on. We'll do this 1,000 times. We'll do it 10,000 times. I mean, when we're talking about this, when mathematicians are doing this, they do it 1,000,000 times. And hypothetically, it should be an infinite number of times. In some ways, what we're doing here is similar to what's called in computer science Monte Carlo testing. We start with a population that we know, and then we say, let's see what happens if we take out samples of 2 and plot all the possible means for samples of 2. Let's see what happens with this known population. What would happen if we plotted the means of samples of 4, okay, so on and so forth. I'm hoping you see this progression. It might be worth watching this again. This is a difficult concept, but it lays the foundation for what we're going to do next, which will be much cooler, okay, much more theoretical. Much less theoretical. So we're at our samples of 8, okay? We're going to keep doing that. Now, here's a question, another question I would pose to the class, and I'll give you a moment to think about it. What would be the lowest value that we could get for a sample of 8? The lowest value for the mean that we could get for a sample of 8. Now, when I do this in class, somebody's going to raise their hand. Oh, 18. And no, it can't be 18. You're getting a sample of 8. You could get a score of a block with 18 on it, but that has to be added to 7 other scores, right? We can't have 8 18s. We're going to pull out the 18, then other blocks. So here's the answer to the question, right? What would be, did I say the lowest? What would be the lowest value that you could get with a sample of 8? I mean, do the same question. I could say, what would be the highest value you could get? What would be the lowest value you could get? We're going to do both. What would be the highest value you could get for a sample of 8 blocks? Well, that would require me to get the 18, my ink's running out here. That would require me to get 18 plus 17 plus 17 plus the 3 16s plus 1, 2, 3, 4, 5, 6 plus 2 15s. Everybody with me? To figure out what would be the highest mean of 8, I would need to get the highest 8 scores. To get the highest mean for a group of 8, I would need to pull out the highest 8 scores. Extremely improbable to do that. We could do this 1,000 times. Now I would bet $200 that we're not going to get this mean, okay? But I've calculated that, and that would give me 16.2. These numbers give me a mean of 16.2. That's the highest value for the mean. Likewise, for the lowest value, we'd have to get the 10, the 2 11s, the 3 12s, and 2 of the 13s. I've calculated that. That would give me 11.7. So the lowest would be 11.7, and the highest would be 16.25. Let's do this. Most of the blocks will be in between them and really toward the center, and we have a distribution that would look like this. Okay. Guess what the mean of this distribution would be? The mean of this distribution would be 14. That's just what's going to happen when I do this 1,000 times. Now, I hope everybody's good. I certainly would wait for a question here. If you have questions, email me, please, okay? But maybe watch the video again. I hate to say that, okay? You have other priorities, but watch it again. You can read this in the book, but what we see here, these are just, the blocks here are sample means. Blocks here are individual scores. Take out the samples, calculate the mean, we get these, okay? The mean for each of these sampling distributions of sample means will be equal to the original population mean. That's a fact, okay? I'll elaborate on that more in the next video, but that's what happens factually. But here's a question, and I just want you to look at these graphs and pay attention to the highest and lowest numbers that we would get for each of these distributions. Know that that's the highest and the lowest, but most of the blocks are going to be in between there. I mean, the vast majority. But do you see a pattern here that's developing? Do you see a pattern? Hopefully the answer is yes. And the pattern is, as we increase the size of our samples, what's happening to the standard deviation of the sampling distributions? As we increase the size of our samples, with an S, as we increase the size of our samples, what's happening to the standard deviation, to the variability of these curves, right? As we increase the sample size, the standard deviation of the sampling distributions, take it slow. You don't need to rush it. You don't need to rush it, okay? Let your thinking happen, because we speak way faster than we think, right? So the variability, the standard deviation of these sampling distributions is getting smaller as we increase our sample size. The variability is getting smaller. That is, the sample means are coming inward closer to the overall mean, okay? As we increase the size of our samples, the variability of these sampling distributions of sample means gets smaller. Everybody see it? The means stay the same, but the variability around that mean gets smaller. And this is a fact, and this is what happens. And it's so important that we have a special name for this, what we're seeing here, what we see develop. And we would do this in class and see this develop, okay? It has a name. Let me get the sheet. It's called the, I'm going to take this, too much distraction there, right? It's called the central limit theorem. It's called the central limit theorem. Not the central limit theory, it's not a theory, okay? This is a theorem in math. And what it tells you is, this is in symbols, what we just saw. That's why I want you to see it. I'll show it to you again, right? Here we go. The mean of the sampling distribution, of any sampling distribution, the mean of a sampling distribution will be equal to the mean of the distribution of scores from which the sample was taken. And it's like, oh my God, Dr. Specht, can you repeat it? Can you repeat it? And I'm like, I will repeat it, but I want you to see it first. We just developed this. It took us 45 minutes, okay? The mean of any sampling distribution of sample means will be equal to the distribution of individual scores from which the means were taken. Yes, I'll say it again. The mean of any sampling distribution will be equal to the mean of the distribution of individual scores from which the samples were taken. In a way, this is your cheat sheet. If you understand what these symbols stand for, you got it. This is the mean of the individual scores. This is the mean of the sampling distribution. Okay? And I think I want to stop there. There's a second part. But it'll take a few minutes to develop that, and I'm going to try to keep these videos to 45 minutes. So we're going to stop right there. Next video, we'll absolutely go back to that page. I'll review just a little bit. We'll get to this. Then I'll show you how we use this. It's really cool. But we sort of have to know this first, okay? I'm sorry. Well, I'm not really sorry, as you know. But take your time with this. Watch the video again. Make sure you take good notes. Please think. I'm always going to ask you to think. It will make it easier. This is not cookie cutter. This is not something you can just write down and put on a flashcard and memorize. It doesn't work that way. You guys know that. You've already been through half the class. So listen, take care of yourselves. Email me with questions or concerns that you have. Be safe and try to stay healthy. And we'll keep trying to maintain a good attitude. It's hard for all of us. It's hard for me too. We're all in this together, I hope, and we're going to come out the other end, and I'm hoping we'll be stronger. So, love your family too. Okay, have a good day. See you in the next video.